place is always good. What have they got there that's so good?
That's what I'm saying.
The chicken sandwiches, is that?
It's good.
Yeah.
Well, I mean, I'm not against the place, but I'm not gonna wait an hour and a half for food either.
Plenty of order online. So we're gonna get out
You
there.
guys are ahead of me.
Let's find out Wednesday that they have a large sandwich. I think it's good. Didn't know that existed.
Let's see, my book. That phone shuts off and turns on all the time, and I have no idea why. Look at that. Yeah. All right. Any questions about the homework before I start?
Yeah, can you do problem 10?
Yeah, I think so. Give me the information.
It's 1 centimeter long, 1 millimeter diameter copper wire is used as a Hertzian dipole radiator at 1 gigahertz.
All right.
It wants you to find the radiation resistance and estimate the
R
R
dissipated.
dissipated by considering the skin effect resistance of the wire.
Right. And what else?
And find the efficiency, and also find the maximum power gain.
Okay, we didn't talk about gain, that was the topic for today, but let me just show you something. Whenever you deal with any real wires, they have a finite resistance. And you remember back in EMAG 1, you learned about skin depth. You all remember that? All right, so the way you look at this wire, I'm going to expound it. You look at it as just a long tube or cylinder of length L. Now, if you think about the resistance of a long tube, normally you do this, and it'll work for us. You're going to put a conducting surface there and a conducting surface there. This has some sigma. That's sigma of copper, right? Normally, the DC resistance, if this is plus or minus V, there would be this is V, it would give a current, and RDC would be given as the length over sigma times the cross-sectional area. If the wire had a radius A, it would be divided by sigma, right? And then it would be pi A squared. This is called the DC resistance. It's as if the current would uniformly distribute over the actual surface. Do you remember doing this problem? The classic way, just to recap, normally you assume something, you assume I, and then you get J, call that the Z direction, and J would be equal to simply I over pi A squared AZ. After you have J, then you get E, and E would be equal to J divided by sigma, and that would be equal to I over pi A squared sigma AZ. And then once you had E, this is E right here, you would find the voltage. You only care about the magnitude by integrating from 0 to L of the E field dot DL. And that means you would integrate from 0 to L I over pi A squared sigma AZ, and then you would have dot DZ AZ. And when you would do it, you'd end up getting just the L operator here. AZ dot AZ is 1, so it becomes I L over pi times A squared sigma, and that's equal to the voltage V. Now, you remember doing this, right? My last step is to get the resistance, right? To do that, what do? Divide by I, and now I have the resistance. So the moral of the story is when you have something of constant cross-section, the resistance is proportional to the length, inversely proportional to the cross-sectional area the current goes through, and inversely proportional to conductivity. Now, if there's a skin effect, and so for copper here, sigma of copper is equal to about 5.8 times 10 to the 7th and it's 1 over ohm meters. You can look that up in the back. Does he have 5.7 or 5.8? About that. Now, it's not, there's variations with things that are added. They sometimes have an alloy, but that's close. So now what we end up doing is saying there's a skin effect. So we have to calculate the skin depth. And the skin depth is 1 over the square root of pi f mu sigma. I think we talked about that in another class too, right? And that would be equal to 1 over the square root of pi, and it's 1 gigahertz times 10 to the 9th, and then it's times mu, which is equal to 4 pi times 10 to the minus 7th, and it's times sigma, which is 5.8 times 10 to the 7th. And can you just tell me what that is? I see the 10 to the 7ths go.
Actually, in the book solution, it does 5.8 times 10 to the minus 7.
That's wrong. That's an error. Conductivity is about 5.8 times 10 to the plus. Minus 7 would
Yeah.
be no, there's a mistake.
He was doing some sort of weird unit conversion. I actually have a question about that. But
It's got it in the back, it's not since it's 7.
Okay, that's right. This is I'm using MKs, meters, kilograms, seconds. I'm not using some English units or something like that. So what do you get for this? Just give it to me. Anyone? What is the skin depth? We need that to do this problem. Do you have it? No? Anybody?
I guess mine wrong.
I just need this value here. If you go 1 over square root of pi f mu sigma, it's mu naught, by the way. What do you get?
.09 times 10 to the minus 6.
That's really 2.09 micrometers. Microns.
That's what I got.
Now, once you have that, you'll notice that the radius A, he gives it 22 gauge wire, is that right? Did you say 22 gauge?
It doesn't give a wire, it says 1 millimeter diameter.
Oh, he gives you diameter, all right. So this is 1 millimeter, the diameter is 1 millimeter, and that means the radius of the wire A is simply 1/2 a millimeter. I'm just trying to say the radius of that wire, right? So now what we do is say, when we're dealing with skin depth effects, we're going to say we have the same tube here, the same wire, but all the current is going to be contained within 1 skin depth of the surface. So this is equal to a skin depth right there, and the radius is still A. And now what we do is we have basically a thick pipe, maybe not so thick pipe. And now we want to know the resistance from this end to this end, really with the current flowing into the shell around it. You all see what's going on? It's flowing between this and this. So the way we can get this, the resistance, this is called the AC, or high frequency resistance. It's still proportional to the length, right? It's inversely proportional to sigma, but now the area that the actual current flows to is really the perimeter times 1 skin depth thick. So that means it's going to be equal to 2 pi times the radius, which would be 1/2 times 10 to the minus 3. It's 1/2 of a millimeter. It's that, and then it's times the skin depth here, which is 2 microns. I'm just going to use 2 times 10 to the minus 6. Now, this will give it to me. And again, let me put all the values down here. So R high frequency is equal, what was the length of the wire again? 170?
Centimeter.
So it's 10 to the minus 2. This is the actual values. Conductivity is 5.8 times 10 to the 7th. Then you have really pi, because the 2's cancel. Then you have 10 to the minus 3rd. And then you have 2 times 10 to the minus 6. So what does this come out to? This would be the high frequency resistance.
.026.
Is that right? Okay. 0.026 ohms. Can you check that? Is that right? That seems a little high, but I believe you. Is that right, class? Did anybody else do this calculation? You asked about it. Is this the calculation you did for resistance?
I didn't do the problem, I didn't know how to do it.
Well, you know, the only thing you're doing is you're looking at the AC resistance of that wire. It's an antenna, right? So it's got currents flow, and you assume the current's a constant. This would be the resistance the current sees. Does this make sense to everybody? Because it's at a high frequency. Is everybody all right with this? I want to make sure I'm not assuming something. It's just a piece of wire, but now at that frequency, all the current flows in one skin depth near the surface, right? Okay. Now that's DC and that's AC. You want the AC resistance. You're dealing with antennas generally. Now, after that, we need the radiation resistance because he asked for it. So R rad for a short dipole. I think you remember this. This was 40 pi.
80.
I'm sorry. 80 pi squared, and then it's length over lambda, right? Length of an antenna over lambda. So what is lambda? Well, lambda is equal to 3 times 10 to the 8th divided by 10 to the 9th, or it's 0.3 meters, right? So now, well, 0.3 meters is what? 30 centimeters, correct, class? So now we get the AC resistance is 80 pi squared, and then L is L is 1 centimeter, it's 1 over 30 squared, and what do you have for that?
0.877 ohms.
Not very much. Now that we have that, the next thing we do to calculate the efficiency of the antenna, what it really amounts to is this. Efficiency, I think the symbol is still epsilon. This is efficiency. That's equal to the power radiated over the total power radiated plus power dissipated. Follow me on this? Efficiency is always, if it's 1, it's always multiplied by 100. You could get percentage, but it's always total power radiated over power radiated plus power losses. So it's power dissipated by the resistive heating in this case. Does this make sense to everyone, class? All right, well, when I look at this, the same current is going to cause both effects. So this, the efficiency is really power radiated is 1/2 times the radiation resistance times I squared over power radiated 1/2 radiation resistance times I squared plus the R dissipated. That's 1/2 R, really R, 8 R high frequency times I squared. Does everybody agree with that? I'm just defining the power. You're going to notice the I squared is then 1/2 cancels. So really what you get is the efficiency is equal to simply R rad over R rad plus R high frequency, or really the AC resistance of the wire. And for our case, what does it come out to be? It's 0.877 over 0.877, right? Plus 0.062, 0.06, or 026, pardon me, 026. And what do you get for that? It's pretty high.
97%.
Is that what the book has?
Yes, sir.
All right, that's how you do that, bro. And what else did he want?
Just power gain, max power gain.
For what current? They have to give me a current. Oh, they power
It's just
gain.
efficiency times the D max.
Yeah, I mean, but we didn't get into the
Yeah.
directivity yet. We're gonna do that today. So directivity is something I'm about to talk about too. All right. Are you with me with this so far? The key is understanding how skin depth affects your radiation, your resistance, and your losses. One other thing, I think I mentioned this before, but when you have high frequency applications, when I was doing my graduate work or my master's work, it was I was using a 13.56 source, megahertz source, 13.56 megahertz source to create a plasma. Well, the 13.56 megahertz source had piping that was all hollow. And the reason is all the current hugs the surface. So having any metal in the center would just be a waste. So what they did is hollow it out, and they had water run through the center. It was distilled water to cool it. because this is a plasma reactor and it gets hot. That's how they did it, which is interesting. All right. Now, any other questions about the homework?
Yeah, on 8.8,
Okay.
it gives you, the vector magnetic potential of like mu naught I naught e to the minus j beta y.
Let's do it. Yeah. This one. What I'm going to say is this is the important thing about the magnetic vector potential, that to get the H field, or I mean the B field, and then E, you have to know these relations. I pay attention because you got a quiz coming up. So if you're given A, right, magnetic vector potential, then if you want B, it's equal to the curl of A. It has to be in the coordinate systems that's stated, right? After you get this, you get B. Well, B is equal to mu 0H in free space. Agreed? Right? And we know that therefore H is equal to curl of A over mu 0. We did this last time. I developed the actual Helmholtz equations for voltage and A, right? And then if you take a look at this, I know curl of H, right, is equal to usually J, but if you're not where there's a source, J is 0 if you're far away, and it's going to be plus J omega epsilon times E. So now I could say that E is equal to 1 over J omega epsilon times curl of H, but A is equal to curl of A over mu. And this is the electric field based on the curl operations. Are you with me?
Yeah, so for A, will you give us an equation for A based on what coordinate system?
Yeah, and you can take a look at it. If it's X, Y, and Z, you do the curl in X, Y, and Z. If it's anything else, whatever. So, I mean, I would never ask you to memorize all the curls for cylindrical and spherical coordinates. But for Cartesian, it's relatively trivial. It's actually not bad for the other coordinates. I just don't want people focused on memorizing those things. If you look at, well, give me the problem. Give me A.
Mu naught I naught e to the minus j beta y.
Mu naught, I naught, oh, go ahead.
E to the minus j beta y.
Beta, Y, over?
In the AZ direction. Over nothing.
Over nothing? All right.
Yeah, that's what I was confused about.
Well,
'cause-
that's just a fictitious one, but that's okay, because, well, I'm not saying, maybe there's a possibility over a small region of space you could have this, but this is a weird one. Anyway, what he does is gives you a constant times e to the minus j beta y, right? Now, please follow me on this one. The curl operator, the easiest way to get a curl of A in Cartesian coordinates, you all agree that that's only the AZ component, just by looking at it, right? Well, what is curl? The curl of A is equal to, I like it as a determinant. First, you put the unit vector symbols. Then you put the derivative operators. And then you put the values of the vector components, AX, AY, AZ. This is called a determinant. Y'all remember determinants back in the day when you had your calculus courses? Well, here, we kind of strike it rich because we only have a Z component, right? So we get rid of those two. And now if it's only a Z component, look, I have AX ddy of AZ. So it's going to be AX ddy of AZ. And it's also going to be what? Then when I go this way, actually here, here, and here, then it's going to be minus AY. Do you remember how to do this? You go up. Normally, you'd rewrite these first two columns. You're going to come here, here, and here. Do y'all remember that? It's minus. How many remember doing this? All right. It's just the standard curl operations, right? Using a determinant. So this is going to be, now I'm going here. This is AZ, Y, and AZ. And I'll tell you one other thing. Here's how you always remember this. This is AZ here. AZ, and it's ddy of AZ. Do you agree with me? All right, now take one look at that. forward. Wait a second.
Sorry.
That's AX, DDY, and AZ. I take it back, this is DDX. My bad. Then you come from here to here to here, and this is AY2.
Are you doing the AX component?
This is AZ, but if you look, when you do a determinant operator, let me go ahead and do something. Normally what they say is you rewrite the first two columns and it would be AX, right? And then it would be AY, and then you would have DDX, and then you would have DDY, and then you would have 0 and 0. Those are the first two columns, right? Now here's how it goes with determinants. You come down this way, those are all plus. So it would be AX, DDY of AZ. Then when you go this way, it's all negative. So it's going to be minus DDX of AZ, and it's in the Y direction. Y'all see what I've done there? Isn't that how you were taught? When you did determinants?
Yes, one way.
There's tricks to do this. They say this is positive, this is negative, this is positive, and they did just the they did like a multiplier this way times this way of what's left down there. I don't know if you were taught that, but do you all remember this kind of stuff? It's fairly straightforward. Now, what is this is my point? Well, does AZ vary with X? No, just the Y component, right? So that means I have minus J beta, right? When I take a derivative of that with respect to Y, I get a minus J beta. Then I have mu 0, then I have I naught, right? And I have e to the minus J beta Y, right? And you'll notice that the direction of that thing, that's AZ, with respect to Y, is an AX direction. So that is the curl of A. Let me put it down. This is the curl of A according to the vector operations, right? And what is curl of A? It's B. So this is B. Y'all agree with them? What else did they ask for? E?
Yeah, well, from that, just about a mu naught to get the H, then you can get E.
That's right. And so now, if I want to get H, I can say H is equal to simply B by mu naught. So it's equal to minus J beta I naught e to the minus J beta Y AX. You need the vector sense, right? Now we want to get the E field. And the E field would be, you can just do it this way, put curl of H since I have that. Do you agree with me there, class? Or I should say curl of B, my bad. Right? Here, see, I plugged in this down here. I don't mean to confuse you. If you put this here, you get curl of A over mu naught, right? But that's, let me do it this way. If we just do this, so I don't confuse you. Are you all with me on here at that point? That is assuming that J is equal to 0. I'm in an area where there's no current, no force current. Understand, everyone? Because what? Curl of H, this is Maxwell. This is Ampere's law. Curl of H is equal to J plus J omega epsilon times E, right? And if J is 0, then that's what E is, right? It's J omega epsilon E. So if I want to know what E is, E would be equal to 1 over J omega epsilon times curl of H, which is 1 over J omega epsilon, and curl of H, that's H is equal to minus J beta I naught e to the minus J beta Y, right? And it's AX. Does everybody agree with that? What did I do? I took that information and I replaced H with it, right? Does everybody agree? This is my H, right? And I stuck that in to the curl of H right here. And I still divide by J omega epsilon, correct, class? Now, try to go with me on here. I have a J here and a J here, so I'm gonna erase the J's. Agreed? Now, at this point, I could mess around with beta. I could say beta is omega times square root of mu epsilon if I want, but I'm not gonna mess anymore with these constants. I'm just gonna let that be minus, and that's just a constant right there. Do you agree with me? Are you with me?
Did you take the curl of H yet? Or is that just H?
No, I didn't. Here, let me do that. I didn't take the curl. You're right about that. I'll put 1 over J omega epsilon, and then it's a curl of my H is right there. Sorry about that. Give that to me again. It's minus J beta I naught e to the minus J beta y. It's in the AX direction. I'm very sorry I did that. Are you with me? That should make sense, right? It's the curl of H, and I've just replaced H with that value. Do you agree with me? Now, at this point, I'm going to erase the J's because they appear both places. And I'm also going to take the beta I naught out in front and the minus sign. So now I take this, and I have minus beta I naught out here. Now the only curl I really have to deal with is this term. It's got an X component, right? And it's e to the minus J beta y, correct, class? So that's an AX component. Now I'm going to go back up here and do it. So I know the curl of this, curl of e to the minus J beta y in the AX direction is equal to AX, AY, AZ, DDX, DDY, DDZ. And then, if you take a look at this, there's only an X component, and it happens to be e to the minus J beta y. This is 0 and this is 0. Do you agree with me, class? Okay? All right, now what is that going to be? Well, when I look at this term, I could recreate this row and this row, but I can see if I go AY DDZ of that, just look at this for a second. AY DDZ of this, is there a derivative with respect to Z? You all see it's not, it's 0 because this is only a function of y, correct, class?
Yes.
Then it's going to be what? Minus DDY of this times AZ. So it's going to be minus DDY of e to the minus J beta y. Correct, class? It's just going, this is what they call bookkeeping. You're doing the mathematical operations and you're taking care not to make sign errors and stuff like this. And what's that going to be?
Minus J beta times e to the minus.
Well, the minus J beta, when I take a derivative with respect to y, comes out, but there's a minus sign, so it's just y. J beta, right, times e to the minus J beta y, and it is in the AZ direction. Do you agree with me? Right? So now I come down here and I say that's going to be equal to minus beta I naught, right, over omega epsilon times J beta E. I have 2 AZs, I only need 1. J beta times e to the minus J beta y in the AZ direction. And that's equal to the E field. Do you agree with that?
No.
Yeah. That's beta squared. Now, I don't know how he has his answer. Does he have a beta squared and a j out here? Like that, and get rid of the beta inside? I don't know. I'm just saying that's how you get it. Everybody follow me on this? What don't you understand?
I don't know, I did the, minus intrinsic impedance cross H to get my E.
Alright, that's assuming it's a propagating field, right? Remember when I said that if you have E cross H is the direction of power flow, but if you're gonna use, if you want E by saying minus eta times a direction of propagation, unit vector in the direction of propagation crossed with H, that assumes propagation. That means you're not in the near field. I didn't assume I wasn't in the near field. When you're doing the curl of operators, you get all the terms. Near field as well as far field. Does he have that as his answer? Isn't the answer, didn't I give you that answer? I didn't? No?
I don't
I
think
hear
so.
it.
You gave 2 presentations and then said do 8.7 to 8.10.
It didn't, the answer wasn't given though, huh?
And the book gives the answers to the odd problems in the back.
I'm sorry, I'll make sure I put that up there if somebody sends me an email to remind me. That's how you do it though. Right now, what you did though is you're assuming,
Property.
yeah, and I don't know if the answer's the same.
It's not.
You have to do the entire curl operation.
Okay.
I'll tell you one other thing too. Remember this curl of H of A here, that's the gradient of divergence of A minus del squared of A, and you can, there's tricks with that, but I don't want to spend time on that today. Where you can really manipulate it and get easy answers, yeah.
Is this gonna be what the quiz is on?
Well, it could be on a lot of stuff, but it's anything related to the homework. You gotta understand it, it's related to the homework, always. My quizzes are always related to the last 3 homeworks, 2 usually, 2 prior. That's the way it always works, from the material we cover from Monday till Friday. All right.
It's easy on first.
Did I give you another problem with this, the curl equation? No?
No.
All right. Well, nevertheless, any other questions about the homework? Let me restate something. If you have A, the curl of A is equal to B,
Yeah.
right? And B is mu H. And the curl of H, if we're in if we're a long ways away, where J equals 0, that's no sources, curl of H is equal to J omega epsilon E. And that always works. Those are 2 equations. Those are Maxwell's curl equations, and you must know Maxwell's curl equations to pass EMAC, or you're really in dire straits. It's sort of like trying to get through circuits without Ohm's law. You really can't do it. All right. So next, I'm going to recap the short dipole. Now, I'm going to tell you for a short dipole, the things you got to know is radiation resistance, right? You have to know radiation resistance, the E fields form, and we're going to talk about something called the directivity and gain in a second. But first, for a short dipole, right? Short dipole is something where L, really the length of this, is much less than a wavelength. Really, length less than lambda over 10 is probably the way it's usually set up. So if it's less than 1/10 of a wavelength, it's a short dipole. Now, if we have a short dipole, then we know that the electric field at a distance r from the short dipole, if the dipole is in the z direction, so I always assume the dipole's in the z direction unless there's a reason not to. This E field is given by You'll get to know this real well as you keep doing problems. But this is equal to j eta beta over 4 pi epsilon naught times e to the minus j beta r over r, and then it's going to be times the length, the electrical length L, and then it's times the sine of theta a theta. That's the electrical field. It's in the theta direction. Now this is the far field, right? It's not the total field, it's the far field. We'll get to the near field in a bit. The next thing is going to be the H field from this is, now you can tell me how to, just by inspection, if that's the far field, how do you get the H field? You remember? If you have the E field and you want the H field and it's a propagating wave, what's the relationship thing that I always tell you? Anyone? What is E over H equal to?
Eta.
It's the intrinsic impedance of the free space, right? So H here would just take this and divide it by eta. Well, there's eta, right? So it goes away. So it's going to have the same form, J beta. Oh, by the way, somebody should scold me here. I didn't put the current value in there, I naught. J beta I naught over 4 pi epsilon naught times L times the quantity e to the minus j beta r over r times sine of theta, a theta. So that's the H field, but it's not a theta, it's a what? Phi, right? Now it's not in the theta direction, it's in the phi direction, right? We're in spherical coordinates here. Do y'all agree with that? It's got to be perpendicular, and E cross H has got to be the direction of propagation. Well, E is theta, H is phi, E, and then we have theta, phi, rho. Are you with me? Okay. That's the actual H field. Do you remember what the power density was, SF? You can just put it down as 1/2 the magnitude of the E field squared, right, over eta in the AR direction. It's radially away, and you don't have to worry about calculating more than that right now. Do you follow me on this, everyone? Then, after that, you'll notice the total power radiated, right, is 1/2 the radiation resistance, 80 pi squared, times L over lambda squared times I squared. That's the total power radiated, right? And if we want to, we can calculate the radiation resistance, but it's right there, right? So now the next thing we talk about, and we're not going to actually solve this one using A. I'm just going to set this up for you. This is going to be a small loop. So write down small loop. A small loop means we have a loop in the XY plane, that's the Z-axis, and we have a radius A, and there's a current I flowing around it, as such. What we want to get is the radiated field. Now think about this, in the XY plane we have a loop with a current on it, and we come out a distance theta, at an angle theta at a distance r, and I got to tell you something about this. The electric field will not be in the theta direction, it will be in the phi direction. This is tough for me to draw, but this is the E field and it's in the phi direction. Something else I'm going to tell you about the electric field to give you more of an appreciation of it. You see how the current is vertically oriented? Now, the electric field will always have a component in the vertical, not horizontal direction. If I come out any distance r away, just think if I'm looking at you, I've got a current like this. If I come out a distance r away, the electric field will always have a component along this axis, not against the parallel axis, all right? The electric field will always have a component oriented in the direction of the current. So if the current's this way, the E field is this way, either up or down. If the current's this way, the E field is this way. Follow me? It's important. Now look at that current in the XY plane. It's going like this, right? That means the E field has to be in that plane too. It has to have a phi component. This is an important thing, remember that. Alright, that's the way, you can always do these polarization tests. If you got a short, say half-wave dipole antenna and you're holding it, and you got a polarization filter there, whereas I rotate that filter, or if I rotate this horn and rotate the antenna and hold the actual polarized filter up there steady, then I will see a peak power and then no power. Peak power and no power as it rotates through. Because a polarization filter allows only light of one polarization, or I should say electromagnetic energy, of one polarization to get through. So if the filter's allowing polarized light this way, or electromagnetic energy, and I move my antenna this way, nothing gets through. You follow me? And that's real important. That's a polarization filter. Anyway, for this E field, Dr. Wentworth, he tries to give you a him-hum about what actually is going on. He tries to get the magnetic vector potential for this one, and then from that derive the E field. But he goes right out and says the mathematics are ugly. I mean, it's a series expansion, and yeah, it's a manipulation that takes some time, and it's beyond the scope of the text. So he says if we're given distance r, he's just going to tell you what it is. And I think he has this, the 320 pi squared, and then it's going to be the surface area of that over lambda squared. Actually, I'm thinking about something now. You might, I'm giving you the radiation resistance. Hold on for 1 second. The way I teach this in EMAT and in my EMC courses, I want to tell you this. You see this constant here? That's a single number. I just replace all that with a single number and use it. Here, we're going to find this is a single number, and I don't remember what it is exactly off the top of my head. So I'm going to go ahead and write it down. Oh, this is equal to omega mu is, or I, the current, times the surface area that I'll get to times beta over 4 pi r times e to the minus j beta r, and then it's going to be times the sine of theta in the a phi direction. So that's the E field. I want to just tell you one thing. S here is equal to pi a squared. It's just the area of the loop. S is equal to pi a squared. Are you with me on that? I'll tell you one thing about this that makes it very interesting. Now, when you look at that, and you look at the short dipole, here's the electric field for the short dipole, right? You'll notice it's proportional to the current. That's proportional to the current. It's a function of the sine of theta. You all see that? And furthermore, no, that's actually all I need to say. It's proportional to sine theta, inversely proportional to r, proportional to current. The other stuff around here are just constants. They're relative constants. Now, a couple things I want you to notice about this. How much power or electric field is going up the z-axis? What's the value of the electric field anywhere in the z-axis? Well, what's the angle theta on the z-axis? It's 0. Take a look. What is sine of 0? 0. There is no electric field up and down the no radiated electric field up and down the z-axis. Do you understand that? It's the same way here. There is no electric field up and down the z-axis. Where is it a maximum holding r constant? Say we have r at 100 meters. Where is the electric field in terms of an angle of maximum? 90 degrees. That's called broadside radiation if it's a dipole. Here, where's the electric field maximum? Right in the xy plane, right? Or at theta equal 90 degrees also. They have the same radiation characteristics in terms of their intensity. The E field's it's polarized in the opposite direction, all right? What would the magnetic field be here, by the way? Just take a look at that. It would be the electric by eta, right, in terms of magnitude, wouldn't it? As a matter of fact, you can say the H field, now H will be in the theta direction, but it's actually minus E phi divided by eta naught, and it's in the A theta direction. So you take the scalar value, take all that stuff, divide it by eta, and put a minus sign, and you get the H field. And the reason that H field has a negative is because when you take this cross this, it has to have a radial component. So if I take A phi and crossed it into A theta, I would get minus AR. That's the reason that's minus signs there. Do you follow me, class? Everybody? Remember, the way you order things in spherical coordinates, first is R, then theta, and then phi. So with the cross product, here, 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 and back again, all positive. But if it goes here, 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 and back again, negative. Follow me, class? Okay, are you with me? Anyway, that's the value of E phi and H theta. Now the small loop antenna, by the way, when I say small loop antenna, you should ask yourself, what does he mean by that? And what it means is the diameter, or 2A, is much less than a wavelength. Because the minute that loop gets of the order of a wavelength in diameter, things change rapidly. Then it doesn't act like it. Then these characteristic equations go out the door. Are you with me? And it's just like you're going to see for a short dipole. As the wavelength approaches the length, the radiation pattern changes markedly, all right? Remember that. It's all about what things are relative to the wavelength, the length of the antenna. Now the radiation resistance of this, he puts it down in his book, but it's really, just put this down, the radiation resistance for a short dipole. This is, for a small loop, is equal to 320 pi to the fourth, and then it's S over lambda squared ohms. Now, you'll see that in his book, but remember, S is the surface area. It's really the area contained within that loop, the loop's circumference. Do y'all see this, class? Somebody should ask me, do I need to remember this equation? Answer is no. I'm not gonna. By the time you get done with every possible antenna configuration, you'd have a lot of equations, and just memorization of it's no good. You have to know how they actually kind of behave. Are you with me? All right, but that's the radiation resistance. And now, I'm going to go ahead and do the dipole. Actually, I'm going to do, I'll do the dipole, then gain, and give you a quiz. Do you guys mind the approach I take to teaching when I do problems at the beginning of the class? I'm trying to figure out the best way to really teach a small class like this. Problems are usually, in my opinion, the best way to get rid of uncertainties, to clarify things. Find a couple of problems that are confusing, do them and talk about them. That usually helps. All right, next. The next thing we're going to talk about, and this is going to be a long dipole. So put down long dipole. Now, when we have a long dipole, the only thing it means is now L is of the order of a wavelength. So here's what it looks like. Now we have something of length. I'm going to use capital L for this. Usually what we do when we talk about dipole antennas, we don't have to do this, but we feed them in the center. All right, so it's a balanced feed. It means the same length of wire is above it as below it. You don't have to do this, but believe me, there's not a lot of reason not to. It makes everything symmetric, for one thing, and the impedance is symmetric. It's a long story, but trust me, this is the way you want to feed an antenna if you're given a choice, unless there's an extremely important reason why you wouldn't. So when I do this, let's call this 0 and call this the z-axis. The actual current distribution looks like this. If I was to plot the magnitude of I of z here on this axis versus this height, I would get this. it hits a peak right here, and that would be I naught. And the equation for this current, by the way, the solution for this is not a closed form solution. The way they actually solve this is they solve the Helmholtz equation, the del squared A operator, set things to the boundaries, and they literally solve for this current, but I'm not gonna do that. I'm just gonna say that's what the current is, write this down. So IZ on a dipole is really equal to I naught, and then it's gonna be some e to the j alpha, because this current could also have some phase. Dr. Wimmerspoort includes this. Usually I always make alpha 0, but I'm including it. Then it's times this, the sine, it's really the sine of beta times L over 2 minus the magnitude of Z. In Dr. Whitmore's book, he will not put magnitude of Z, he will say for greater than Z, it's just beta times L over 2 minus Z. For less than Z, he will have beta times L over 2 plus Z. He'll break it into 2 parts. I just put magnitude, forget it. All right? Here's where it gets interesting. So that's I. Now, try to work with me on this one. You're not responsible for doing this integral, but you have to appreciate what's going on. Next, I take a little chunk of current right here of differential thickness, call it dz at height z. You all see what I'm doing? I'm going to take a look at this little chunk of my current, and I want to say what is created. Well, if I come out a distance, try to make this a little better. If I come out a distance r, and there's going to be an angle here, theta. Now this r is right from the origin. And I'm looking at the E field out here. Or better yet, the differential E field out here. Well, my differential field is caused by this current, right? This chunk of current, right? So now I draw a line or a radial vector from there to there, and we call this r prime. Matter of fact, let me do one thing. I'm going to put this a little higher up for a reason. I hope I don't confuse you. What I'm going to do is this. I'm going to make my little differential chunk up here for a reason. So this is going to be dz thickness, and it's at a height z. And now I draw a vector from here to here, or draw a line, and I call this r prime. And I want you to take a look at this just for a second. We assume that r is much, much, much greater than the length of the antenna. In other words, we're a long ways off. It's like if I've got a toothpick up there at the exit sign, and I'm looking at a radius distance from that toothpick at the exit sign back there to me. That's the kind of proportions we're talking about, or greater. Follow me? So if that's the case, you can say that these two, r prime and r, are basically parallel. You all with me? It's like looking at a star. If you're looking at a star and you go 5 feet over, everything, azimuth and elevation is the same. It doesn't change. You're so far away from that star. Do you follow me? So this really means that these two are about parallel. And if you look, the distance difference is this, right? If those two are parallel. And what is this distance? Well, this height is z, right? So it would be z times, if that's theta right there, it would be z times the cosine of theta, right? So now I can say that r prime is actually equal to my r minus z times cosine of theta. And again, this is theta. This is right here. You can look at this in the book. And as theta goes to 90 degrees, there is no difference in r and r prime. Isn't that right, class? When you're straight out, those two rays are parallel to each other. There's no difference in distance. So now I say what dE is. Now we take a look at this as causing the electric field from a short dipole. So we simply put J eta beta over 4 pi epsilon naught. Then we take it and put e to the minus j beta And here it's R prime, which would be R, right? That's R minus Z cosine theta divided by R, and that's really R minus Z cosine theta. I'm gonna clean this up in a second. Normally it was just e to the minus j beta R over R, but the fact is that my R prime would go here, and my R prime is this. Then it's gonna be times the value of I, which is I naught e to the j alpha times the sine of beta times L over 2 minus the magnitude of Z, that's beta in here. And then it's times dz. Just appreciate that's the differential field and it's in the A theta direction. Does that make sense to you? I'm just taking a look at that chunk of current as a dipole, a short dipole, and I got the field. The dipole's length is dz, right? Now, if you look at this, here's the fact. If I'm a long way from this, 1 over R is about 1 over R prime. Do you agree with me? If you're a long way, a mile and a half away from something an inch long, say, then R is about R prime. And down here, we don't even bother putting the Z cosine of theta. We just leave it as R. Now, up here, what I can do is, I can separate this. I have e to the minus j beta R times e to the plus j beta Z cosine theta. Does that make sense? Right? Follow me? When I have an exponential, so I can break these up into 2 exponentials. Do you agree? Also, what I'm doing? Let me do it right here for you. So now I'm going to take all the crap that I'm not going to use out front, and I'll have j eta beta over 4 pi epsilon naught. Then I'm going to have I naught e to the j alpha, and then I'm going to have e to the minus j beta r over r. I like those brackets. And I have my alpha, I've got that. So then I have this integration left over. I have e to the j beta z cosine of theta times the sine of beta times L over 2 minus the magnitude of Z. And I have this dz, and Z goes from minus L over 2 to L over 2. Please appreciate it. I'm trying my best here to get this out. Are you with me? I just took everything that varies substantially over dz from minus L over 2 to L over 2 and put it inside the integration. Now here's the trick on this one. I want you to just listen. He does it right there. Do you see it in your book? What page is it? Which one is it?
Page 450.
Is that what you have, 450? All right, he does it with H though. I'm doing it with E. All right, he has the differential H. Now look, guys, see this right here? This is the bugaboo. What do you think I'm going to do with that? Take a guess. Now remember, theta is constant, right? It's dz, we're integrating it. Well, if I use Euler's on this, remember what sine is? Sine theta is equal to e to the j theta minus e to the minus j theta over 2j, isn't it? Remember that? I see this glassy-eyed look. No, not really. It is. All right. When you do that, then you get a simple exponential integrations for that. All right. And you can do them. I don't have time to do them right now. When all's said and done, you're going to get an electric field. Write this down. You're going to get an E field in the theta direction that's equal to J times 60I naught. That's the magnitude. And then it's going to be times e to the minus, or minus j beta r over r. This should be in his book. Then it's going to be times, he won't have this quite like this, but write it down this way. Cosine of beta L over 2, it's beta L over 2, that's L, times cosine of theta minus the cosine of beta L over 2, all over sine of theta. This right here, all that angular crap right here, this is called the pattern, and in his book, it's really f of theta to the 1/2 power. So this angle, this right here, this work, yeah, this right here that I'm circling is equal to his f theta to the 1/2 power. He actually squares that because it's a power calculation. Are you with me, class? Now, you're going to read this section and do some stuff for me on Monday. But at this point, I'm going to stop and give you a quiz. And so spread out at least the desk empty seat between you and your neighbor. Did you have tests today, anybody? There's a test in signals and systems, I know that. No tests? We can actually agree on what our test is. Remind me on Monday to vote on it, all right? Well, you know, you guys are gonna pick it, all right? What I do is, it doesn't matter to me. I make them up and grade them, doesn't matter what day of the week. But it should matter to you, you don't want 2 on one day. And teachers, what I had, they never did this. They always stuck in the syllabus, there's where our test is. But I got 3 that day. Good for you.
Dr. Gross likes to have an outline and then always put the test like 2 or 3 days before the outline says. After skipping.
Really?
After skipping sections so that we can do the test.
That's nice. I'll tell you, Wentworth is really, when he hands out a syllabus, man, the test is that day, it's that day.
Yeah.
Put your name on it first.
Comes in with the science sheet cards too.
Who? He does?
Mhm.
Wow. I haven't had that grade since grade school. Sign CD. I guess you can do that so you can take the roll quickly. Somebody's not there, you know who's not. I don't know why he would. Does he give credit for being in class or something?
It's like a point for writing your name.
What?
You can get 2 points for writing your name.
We used to have homework due every class day, so that was kind of your credit for showing up to class.
I used to collect homework, and I'll tell you, I stopped doing that when I realized that people were just copying or having solutions manuals. It was defeating the purpose of homework. You should be trying it hard and knowing what the answer is so you can correct what you've done wrong. You could thank me for spending the time at the beginning of class doing this. And I put the curl down, by the way, there, just out of decency. Yes, I did, but you don't have to use mine, you can use yours.